Hey y'all, it's your personal math teacher, Mr. Boyden. I'm back at it again, and today we're going to our next foray into inference, where we're going to start talking about significance tests, also sometimes called hypothesis testing. Specifically, the things we're going to learn today, we're going to learn how to state the hypotheses, we're going to learn what a p-value is and what it is visually as well. We're going to learn how to draw appropriate conclusions using alpha or an alpha level, and we're going to talk about different types of errors that come up in testing. And I have an example here that is basically what the next unit and a half are about, the next couple videos. This is kind of the big idea, okay? So, and we're not going to be able to answer this question today, but this is the type of question that we're approaching being able to understand. Okay, and here it is. A simple random sample of 415 voters conducted 3 weeks before an election reveals that 223 of the voters favored candidate A over candidate B. The following week, candidate A made a series of controversial remarks. A second poll is conducted, again, a simple random sample, and this time 317 out of 630 voters asked said that they favored candidate A over candidate B. Do the data support the conclusion that there was a decrease in voter support for candidate A, after the controversial remarks were made? Okay, to think about this, sometimes people don't even realize this is an inference question. In fact, the first time I saw this before I was a stats teacher, I didn't even recognize that it was an inference question, because you might go like this. You might think before it was 223 out of 415 voters. Let's see what that is as a proportion. 223 divided by 415. Okay, that's 0.537. And then after, what do we get? 317 out of 630. And that is 50.3, or 0.503. So at first glance, it looks like the support went down for the candidate. But the question is that difference big enough to be a statistically significant difference? Or is it more easily described by features that we learned about with the sampling distribution? Or we might say, is it more easily described just by chance, because it may not have been the same people who we asked, or something like that? That's the question that we're setting out to answer in this unit and the ones that follow. Okay. The first thing that we need to learn is how to think about our statistical hypotheses. Now, I'm calling them statistical hypotheses because if you think of them as being the exact same thing you do in science, then it might make this more confusing. The ones in statistics are a little bit different. Okay. One way to think about this is if we're talking about a criminal investigation. You're a jury member, you're on trial, and if you have jury duty, one of the things they're going to remind you is, hey, just keep in mind, everyone is presumed innocent until proven guilty. So the prosecutor is going to present evidence that would say, hey, this person's guilty, and the defense is going to try to say, no, that's not right, and no, there's this other evidence that says that they're not guilty, and so forth. And then the jury has to come up with what the most reasonable conclusion is. Now, they say that you have to have proof. I think we know that if we look at our justice system, you actually don't have to prove that someone is guilty in order to convict them. But if there's overwhelming evidence, then perhaps a jury would move to convict. Okay, now that's different than math. In math, everything is proven. It's theorems, we have proofs. In statistics, we find evidence that is strong enough that we are convinced, okay? And that lines up with what we learned about with confidence intervals, right? There's no such thing as a 100% confidence interval, but a 95 is pretty darn good. The same thing is going to be true here. Okay, here's what the hypotheses actually are, okay? And this is vocab. If you haven't been writing yet, I want to encourage you to take notes at this point, particularly if you're one of my students. Okay, so the hypotheses, the first one is the null hypothesis. When we see this pair of symbols right here, we say the null hypothesis. So maybe I'll put this in quotes. Okay, and that represents, in the example I gave above, that represents like the not guilty. This is our default. And notice, in a criminal trial, there's no such thing as being proclaimed innocent. Remember, they say guilty or not guilty when they read the verdict. That part does line up with statistics really well. So we never get to say that the null hypothesis, oh, yep, it's true. But what we're trying to show is that it's not true. And what we're trying to show is that it would make more sense to accept the alternative hypothesis. Okay? And that's the symbol for it right there, H sub A. We never say H sub A, though. When we see this pair of symbols, we're going to say the alternative hypothesis. This is the thing we're looking for evidence in favor of. This is the equivalent of guilty. We have lots of evidence, and we're going to say guilty. Now, does it mean that we're guilty, or does it mean that the alternative hypothesis is true? then not necessarily. There's no such thing as true certainty in statistics. So what we're doing is we're taking the most reasonable conclusion based on the evidence and based on the data. Okay. Another thing, and it seems like it might not matter, but it turns out that it might be really helpful to writing these. So you may want to pause the video and write some of this. Okay. It can be helpful to think of the null hypothesis as the status quo or conventional wisdom, or a recent study found that this is true, something like that. And then the alternative hypothesis might represent something that we might not be true. Okay. But we're trying to find out if it's true. Okay. Another thing, and this is something you do get marked down on the AP exam if you get this wrong, the hypotheses always reference a parameter. They never reference a statistic. And we're going to see many examples of that coming up over not only in this video, but also over the next couple of videos that are coming out as well. Okay, let's do an example. Let's do 2 examples. First one, a company claims that 68% of high school seniors will go to college after high school. We suspect that the true proportion is actually, let's say higher. Okay, normally in class I have students pick one of these. Let's say that we picked higher. Okay, and then we're going to write the appropriate null and alternative hypotheses in this example. And the reason we're doing this is to teach you how to get them out of a story problem and also how to write them with the correct notation. So the correct notation goes like this. The null hypothesis, H sub 0, is, and we always put a colon right there. And in this case, they said 68%, that's a proportion. And remember, it's a parameter, so it's P, not P hat. So they're saying this is the conventional wisdom that 0.68 is the proportion of high school seniors who will go to college after high school. Now we're also going to write the alternative hypothesis. The alternative would be, and notice we said right here, I made the decision that we're going to try to see if actually it's higher than that. So the alternative might be that P is greater than 0.68. Okay, and so that's the thing then in our study that we're looking for evidence for. Now, this is not a Sherlock Holmes situation, y'all. This is not like we're going out with our magnifying glass. We're looking for evidence. No, it's like we're going to conduct a study, or maybe we already did conduct a study. And at the end, that's what we're going to be looking for in our data. We're asking the question, do the data provide convincing evidence that actually the true proportion is greater than 0.68? Let's look at the next example. In Western Washington, the typical blueberry yield is 28 bushels per acre. The summer of 2015, though, was unusually hot and unusually dry. And a farmer wonders if the weather that year had a meaningful effect on the blueberry yield. We're going to state the appropriate hypotheses. Okay, so this one, we're talking about a mean. So the null hypothesis is that the mean, and remember, this is a parameter, not a statistic, so you don't get to use X bar. We do have to use mu for this because we're making an inference about the population, not about a sample. So the mean, we know the historical average, and they gave that to us, was 28. And so what we're wondering is if the yield in 2015, the mean in that year was different than 28. Okay, so and I'm inferring that it said that it had a meaningful effect on blueberry yield. So meaningful effect would mean that it is significantly different than 28. Maybe, I don't know, maybe blueberries grow better when it's dry and hot. Maybe they grow worse. I have no idea. And so that's why I didn't pick a direction. Versus right here, we were told the direction, or we picked a direction. Okay, so that's 2 different things that can happen. Okay. These are called one-sided and two-sided hypotheses. Also, it is sometimes called a one-tailed and a two-tailed test. And what that comes from, it comes from the idea of the normal distribution. In the end, we call these the tails or the sides. Okay, this is like a tail area. And so is that over there. Okay, so in the case of a one-sided, your alternative hypothesis is always going to be a parameter that is either greater than or less than the null. It'll never be greater than or equal to. And the reason is because the null hypothesis is going to be that the parameter is equal to the null value. And the null value is just some value that's like the status quo. That's what that's referring to. And a two-sided test we're going to say that the alternative hypothesis is the same as the parameter not being equal to the null. Now, we had an example of one of each of those just a minute ago. Let's go look back. In the first example, that's considered to be a one-tailed test or a one-sided hypothesis. And the second one is a two-tailed test, a two-sided hypothesis, because it could be greater than or less than when we say that it's not equal to. Okay. Now, what about for exam questions? For the AP exam or for my exam, we are going to tell you which one it is. We may do it in couched language that's hidden in something, but actually these examples above told us what kind of test we needed. Okay, and the phrases that gave that away was here it said higher, okay, so the proportion was greater than, and here it was had a meaningful effect. Now, you see how that doesn't say which direction it is? It doesn't say higher, lower, more, less. There's no directional language like that. And so we say, I don't know what the direction is. So we're going to see if it's not equal. Okay, so we'll get more practice with that, but there will always be a clue. And with AP exam questions, there always is a correct set of hypotheses. It's never like, well, write it your own way. What do you think? It's not like that. There will always be a right answer. So we'll practice that more. Okay, now we're going to move on and talk about p-values. The p-value is the thing that we look to see if we had a significant result. We hear about statistical significance all the time. This single value, just by looking at it, will tell us if our result is statistically significant. It's going to tell us if we should reject the null hypothesis or if we should fail to. It basically tells us what to interpret out of our data and what we can infer. Okay, so specifically, the definition of a p-value is the probability of getting evidence as strong or stronger than we did for the alternative when actually the null is in fact true. You could think about it, it's like the probability of it's not accepting, but the probability of rejecting the null hypothesis when actually the null is true. Okay, so we'll get more into that language. I'm using language right now that we haven't even talked about yet. So let me slow down a little bit. And let's get the things that you need to know, because there's like all these definitions, but here's what you must know about p-values no matter what going through this course. If we find that p is small, then we have evidence that makes us favor the alternative hypothesis, because that would mean that the result we got from our study is really unlikely if the null hypothesis were true. So we got a result that's unlikely, okay? And so therefore, the null is probably not true. Now, notice this just says small. We're going to talk in a minute about what small means, okay, and how to interpret that. So don't worry about that yet. But here's what we do, okay? And this says vocab down here, but really this is what we do. And it has vocab in it, or how we interpret. If the p-value is sufficiently small, then we reject the null hypothesis. And if p is not small enough, then we fail to reject. Okay? This is equivalent to saying if p is small, we have good evidence, and we would say that the person is guilty, like if we're in a trial. Okay? And fail to reject, that's the equivalent of not guilty in a trial. And I insist that you write this down. Okay? If the p-value is small enough, we reject the null hypothesis. If p is not small enough, then we fail to reject the null hypothesis. Guys, there's no such thing. A common mistake is people want to say like, oh, so we accept the null hypothesis then. No, we don't accept it. We just don't have enough information to say that it's wrong. Okay, and so that might feel a little weird at first. Okay, let's look at another example. Okay, and this one has the answer right on it. So we'll talk about that. I'm also going to do a visual here. A company claims that 68% of high school seniors will go to college after high school. We suspect that the true proportion is actually higher. In a random sample, we find that 31 out of 40 seniors are going to college next year, and we perform a significance test finding a p-value of 0.018. We need to interpret the p-value. Okay. We'll answer that interpret question in just a second. I want to add something to what we talked about though. This right here would be considered a small p-value. So in this example, without using big language, because that's a really small p-value, that's enough for us to say, yeah, actually, probably it is more than 68% of high school seniors that would go to college based on this, okay? Now, anytime in AP statistics they use this word interpret, basically always there's a specific answer they want. Okay, now remember, a p-value It's like a hypothetical if the null hypothesis were true. Maybe I ought to write out the hypotheses to make this a little bit easier. The null hypothesis in this example would be that the proportion is 0.68 and that the alternative, although sorry, that's supposed to be lowercase a, that the alternative hypothesis is greater than 0.68. Okay, so here's our answer. We're assuming, it's a hypothetical assuming the null is true. So that's what's going to be in this answer. So here it is. Assuming that the proportion of seniors who are going to college after high school is actually 0.68, there's a 0.018 probability that we would obtain a sample proportion of 0.775. That's what this is right here. So the evidence that we did, or higher, in a random sample of 40 seniors. Now guys, that's exactly what we saw not that long ago with sampling distributions. So let me show you what that is. Okay, so basically what this is a normal distribution with the null value, that's the null hypothesis, so that's the null value, being centered. And so we're saying, okay, if that's true, if it's true that we're talking about 0.68 being the actual percentage of high school seniors going to college next year, then what would be the probability that we get a value of 0.775 as our sample proportion by chance alone? And this is saying, according to this example, that it is p-value, which equals 0.018. And that's what this language is of 0.775 or higher. It's saying 0.775 or a more extreme value. Okay, and so that's like visually what a p-value is. Okay, we talked about whether the p-value is small or not small. The way we define small is in relationship to the significance level, which is alpha. Okay, now for AP, they're going to give us alpha typically. They're going to tell us. If they don't tell us, then you can assume that it's 0.05. And the reason why is, remember how in the previous unit with confidence intervals, we said, hey, if we don't know, like the standard confidence interval is a 95% confidence interval. I want you to notice that 95 and 0.05, those are complementary probabilities. And that's specifically why. It's something that's outside the confidence interval is what this is a reference to. So specifically, this is how we use our result at the end of a significance test. If our p-value is small, less than alpha, then we reject the null hypothesis. But if it's too large, that it's greater than or equal to alpha, then we fail to reject the null hypothesis. Okay, let's do an example. Calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers are not getting enough calcium on average. Is that true? So this is a typical AP thing that they do. They'll kind of give us a scenario, like, is it true at the beginning? Just so you know, when they do this, they're not actually asking that question. They're just getting you in the right headspace of the question, that that's the type of thing that we're grappling with. Okay. They want us to state the appropriate hypotheses for performing a significance test, and they want us to define the parameter of interest. All right, parameter of interest. Let's do that first. The parameter of interest is, now that I noticed I said right here on average, so it's the amount of calcium on average. So I'm going to go like this. Mu is it's calcium intake for who? For teenagers. So it is the average daily calcium intake. Whoops, got to spell daily correctly. Calcium intake for teens. Let's write out our hypotheses. The null, that's going to be that mu is, so they recommend 1,300. That's kind of our benchmark value. That's going to be our null value. And then our alternative is going to be that mu is, now let's read this carefully. They said they are concerned that teenagers are not getting enough calcium. So that would be less than 1,300. So they want to know, is there evidence that actually, so we're worried about that. We're going to go see if there's evidence that actually teenagers are not getting enough calcium. Now, let's keep going. Researchers decide to perform a test using the hypotheses stated in number 1. They ask a random sample of 20 teens to record their food and drink consumption for a day. The researchers then compute the calcium intake for each student, and the data analysis reveals that mean, the sample mean, x bar, is 1,198 with a sample standard deviation of 411. And they performed a significance test and got a p-value of 0.1401. And they ask us, what would it mean for the null hypothesis to be true? So the null hypothesis is up here. Now remember, that mu is the parameter. It would mean that teens, on average, they get the recommended calcium intake of 1,300 milligrams per day. So teens, on average, get the recommended 1,300 milligrams calcium per day. And then the alternative, if we get to the alternative, then we're going to be saying they don't get enough. Okay, now we need to interpret the p-value. I think there are different ways of wording this interpretation of the p-value, but it has to have these certain components. It has to reference the null hypothesis being true and the probability of getting a value that we got in our sample or a more extreme value. So the way I wrote that out for this one is, if the mean daily calcium intake of teens is actually 1,300 milligrams, then the probability of getting a sample mean, which is x bar, of 1,198 or less is 0.104. Now that says or less. I do want you to notice the alternative hypothesis has the or less, and that's why this p-value is also referring to or less. Okay. Also, I want you to notice that I referenced the actual sample mean that we had, and I referenced the p-value in this interpretation. Those are things you need to do. Now, number 4. What conclusion would we make at the alpha equals 0.05 level? Okay. Now, once you get this down, these answers are always the same, and this is the classic ending to a free response question. And usually we would do all these other steps kind of in the middle and without being prompted, but this is typically how they always end. So we would say this. We say, since the p-value, which was 0.104, or 0.1401, and we have to interpret this now. It is greater than alpha, which equals 0.05. Okay, so our p-value is too large. We fail to reject the null hypothesis is how we write this. Fail to reject the null hypothesis. And then we would go on to say, we do not have convincing evidence that, and then what was the thing we were trying to figure out? So we were trying to figure out if teens were not getting enough calcium. I'm going to scroll up here just a second. So they said the NIH is concerned that teenagers are not getting enough calcium. We don't have convincing evidence of that. It might be true. And in fact, our sample mean sort of suggests that it's true. But we would call this some evidence or weak evidence. Some or weak evidence, because it is a piece of data. You go, wait, but the mean is less than 1,300, right? But we can't really have any kind of certainty, well, not beyond 14% level, that this is not just due to chance. I mean, it could just, you might have just asked the people who don't ingest calcium very much. Okay, so we do not have convincing evidence that teens, on average, do not get 1,300 milligrams of calcium daily. There are other ways to word that. We could have said that we don't have evidence that they're not getting enough calcium. That also would have answered this question, right? So, but you have the point is you have to reference the p-value specifically comparing it to the alpha level that was given. Generally, they'll give you the alpha, and again, if they don't, assume 0.05, the same way we assumed a 95% confidence interval. And then in order to do this, we have to have this phrase, we fail to reject, you have to have that, and we have to say that we do not have convincing evidence. All right. Now, our last thing we're going to talk about today is the error types that come up with this. And this is personally my favorite visual in all of statistics. I love this next one. This is, and I love it because when I learned about error types, I didn't really understand them at first because they were taught to me as like formulas and as big sentences and symbols and things, and I didn't quite get it. But this really just brings it home. These are the two error types that you're going to run into in statistics. The type 1 error and the type 2 error is how we say those. Okay. The type 1 error represents a false positive. And so check this out. You got the guy here, he's in the doctor's office, and the doctor's saying, hey man, you're pregnant, and look at his face. Oh my gosh. Okay, so it would probably be pretty obvious to us that that guy is not pregnant, since, I mean, I guess that would be obvious. And then type 2 error is a false negative, where here's a lady that at least has the appearance of being pregnant, and the doctor is saying, I'm so sorry you're not pregnant, which she's got to be wondering why that is. Okay, so a type 1 is a false positive, a type 2 is a false negative. If I can just be totally honest with y'all, when I answer a question with an error type, I literally pull this like visual of these doctors talking to these patients up in my mind. And just remember, type 1 is the guy saying, hey, you're pregnant, it's a false positive. And type 2 is a false negative. Now, that's kind of silly, although I find it really helpful, and my students in the past have found it helpful. Let's also get the formal understandings as well. So in the context of what we've talked about today, a type 1 error is when you reject the null, even though it's not true. Now remember, to reject the null, that means you found evidence of something. So for this doctor to say that this guy is pregnant, he found evidence of a pregnancy, even though it's not true. Okay? False positive evidence. And that's something that can happen. You can just so happen to get a sample that leads you to a false result. So statistics is not totally watertight, but it is still extremely useful. The fact that it's not perfect does not mean that we should reject it, because it's a really, really useful and good tool, and we've achieved a lot as a society with statistics. So don't be bothered about the fact that it's not perfect. Nothing's perfect, right? So this is just like that. Okay. What about a type 2 error? That's when you fail to reject the null, when in fact the alternative is true. So it's failing to find evidence. So notice this doctor up here who's telling the lady that she's not pregnant, and she's like, but it's kicking, right? Like, so she failed to, this physician failed to find the evidence that this woman was pregnant. Okay, and that's what's going on here. Okay, even though there is something going on. Okay, now, there's multiple reasons why this could happen. The most common reason that you would have an error is it's just a feature of sampling variability. Okay, and we saw that earlier in the course. You sometimes, even with the best intentions, sometimes you just get a weird sample that doesn't match the reality of the parameter. That can happen. Okay, the other thing I want you to know is that alpha is the probability that you have a type 1 error. Okay, so type 1 error is alpha. And please write that down. Okay, so think about that. If our alpha is 0.05, we go into a test, a significance test, knowing that there's a 5% chance that we could commit a type 1 error. Okay, and so if we want to be really, really sure about something, we might think about a significance level that's higher, or if we don't need that level of certainty, then we might consider an alpha level that's a little bit lower if we're doing our own study. Let's try a final question. The manager of a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait for longer than 2 minutes to receive their food after they place an order. Based on store records, the proportion of customers who had to wait longer than 2 minutes was P equals 0.63, or 63%. In order to reduce this, the manager assigns an additional employee to drive-through orders. During the next month, the manager collects a random sample of 250 drive-through times and finds that P hat is 0.576, and we can infer right here that they found that 144 out of 250 customers had to wait longer than 2 minutes from that. The manager then performs a test of the following hypotheses at the alpha equals 0.1 significance level, and there we have the hypotheses. We notice a one-tailed test, and they also define the parameter for us, which we always need to do. The true proportion of drive-through customers who have to wait longer than 2 minutes to get their food. We need to describe what a type 1 error is and what a type 2 error is in this setting. So a type 1 error, remember, that's a false positive, meaning we found evidence, and if we're finding evidence, we're finding it in favor of the alternative hypothesis. So that means that the manager comes out of this thinking that the proportion is less than 0.63 when actually it is not. So basically, the manager thinks that less than 63% of customers are waiting more than 2 minutes, even though it's true. 63% of customers are waiting that long. So basically, the manager thinks things are better than they are. So thinks customers wait less than they do, to put it really basically. Wait less than they really do. Okay, now what about the next one? So a type 2 error, remember that's a false negative. It means we did not find evidence when in fact there was evidence. It's the doctor who's looking at the pregnant belly and saying, I'm sorry, that's not a pregnancy, even though clearly the thing is kicking. Here I wrote that we don't determine that P is less than 0.63 when actually it is. So that would be like the manager thinks customers, so thinks that 63% wait when actually less do. Okay, now this next question is a really important question in statistics. Yes, in AP statistics, but in statistics generally. When we're setting up a study and we're thinking about how to analyze it, we need to think really carefully about which type of error is more serious. And this is different depending on the context. Okay, so it's not like, oh, a type 1 is always more serious. No. It's context dependent. So think about these two scenarios. Which one would be worse for the manager? If the manager thinks that customers aren't waiting that long, but actually they're waiting a long time, or if the manager thinks that 63% of customers wait 2 minutes, but actually not as many do. In order to understand this, think about what the manager's next moves might be based on those pieces of information. If we commit a type 1 error, and the manager thinks they don't wait that, or thinks that a smaller percentage wait than before, then the manager is going to think, okay, well, I'm doing a great job, and things have gotten way better, and this is awesome. We're doing a great job at our drive-thru restaurant. Even though the customers are sitting there waiting, and the manager's thinking things are good. So that's not a good situation. What happens if the manager has a type 2 error, or if we have a type 2 error, and the manager thinks that 63% of people are waiting when actually not as many as that are? Well, the manager is probably going to say, oh no, I thought we improved, but actually we have not necessarily improved. And so I'm going to need to do things in this restaurant to improve the experience for our customers. So this is what we would call a cheap error. The type 2 is really cheap because if we get it wrong, then the result is we end up making the restaurant better. But in a type 1 error, and so 1 is what I'm going to say is more serious, because in a type 1 error, you think your restaurant is better than it is, and you think your customers have a better experience than they do, and so you're not going to take the necessary steps to improve the customer experience, and your restaurant may struggle. Maybe, your customers are going to get fed up and say, I don't want to wait that long anymore. I'm getting sick of this. I'm going over to, McFry shop across the street or whatever it is. Okay. So guys, that's my reasoning for why in this particular case, a type 1 error is the serious one. Okay. Based on our answer to question 2, do we agree with the company's choice of the significance level of 0.1? Interesting. Do we agree that it's okay to have a 10% chance of making a type 1 error? Now remember, guys, that's what alpha is. Alpha is the significance level, but it also tells us the percentage chance of a type 1 error. So are we okay with a 10% chance that we're wrong and that we think that the customers are I keep saying that wrong, that we think that a smaller percentage than 63 of customers are waiting for 2 or more minutes when actually that 63% are still waiting? Probably not. So I'm going to say no. And then the reason is because we said type 1 is more serious. So type 1 is a serious error. And so what we want to do in our analysis of the data is we want to make sure that we try to take reasonable precautions to avoid committing the more serious error type. And so we're going to say maybe alpha equals 0.05 would be safer. Okay, if the customer experience is something that we really care about. Okay, we have this question again of interpreting a p-value, and so I want to invite you to give that a shot. Okay, and they said the p-value of the test is 0.0385, so let's interpret that. If 63% of customers wait longer than 2 minutes, and that's talking about the population of customers, then the probability of getting a sample proportion of 0.576 or less, which is the measured p-hat value we had up above, is the p-value of 0.0385. And so I've added one other question down here at the bottom, and that's asking, what conclusion would you draw at the significance level of alpha equals 0.10? And I want to know how the conclusion changes at 0.05. So let's write like our this is sort of the concluding statement. And this is one we want to practice because nearly all free response questions end this way. Okay, so I'm going to write it like this. Since the p-value, of 0, which equals 0.0385, is less than alpha, which equals 0.10, we reject the null hypothesis. Or you know what? Let's do that symbolically. That'll be even better. We reject the null hypothesis. We have convincing evidence that less than, because that it was a one-tailed test, it was a less than, so that less than 63% of customers, I think it was drive-through customers, so that less than 63% of customers wait longer than 2 minutes. Okay, so you see how this conclusion, it's two sentences. One of them is in context, one of them is just basically a statistics sentence. So the first one, since the p-value, blah, 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 we reject the null hypothesis, that is a stats sentence. You also then always have to contextualize it in the actual question. Okay, now the very last part of the question, how does that change if alpha is 0.05? It doesn't. It would change what we wrote right here, but in this particular case, so be careful. Sometimes it will change it. If the p-value is between 0.05 and 0.1, then yeah, that would change it. But this p-value is less than both of the proposed alpha values. And so everything in this sentence would be the same because our p-value is sufficiently small, we would still be able to reject the null hypothesis. People, that's your friendly introduction to significance testing and hypothesis writing. I hope this video was helpful, and I'll see you next time.